right, so welcome. Maybe some more people will trickle in, we will see. We are going, if you notice the schedule originally said we were going to have a guest lecture today. That has been moved a bit. Hopefully that's going to happen next Friday. I have to confirm things. So we're just going to press on with the types of stuff that you're going to be doing for the next assignment. I know sometimes we're a little bit ahead in the lecture than on the assignments, but that kind of makes sense a lot of times. You guys are in the middle of the keyboard assignment. Hope that's going well. Well, I heard some laughs in there. I'm not. Maybe it's not. The keyboard assignment. Yeah, that's right. Maybe you're not to that one yet. You will be to the keyboard assignment very soon. And then we finally get into. Well, I say finally. The next big thing is graphics, right? So remember, you're trying to create a console program, and you're trying to do it on this raw, no operating system Raspberry Pi. And we have to figure out how to output something to the monitor. Now, it turns out that if you plug in your Raspberry Pi to using the HDMI cable on it directly into a monitor and just turn it on, this pretty little picture comes up. Okay, I will show you some things on the screen too, but most of it will be on the one down here. But this pretty little picture comes up, and we'll describe what that picture actually means, and of course how to change it. Okay, so this whole lecture is on graphics and frame buffers. This stuff gets a little bit into the weeds, but it's actually kind of cool how it ends up working out. Okay, so that's all the stuff you've already done. You are, well, most of you are finishing, some of you are still finishing up Malloc, but then keyboard, you are getting to that. And then now we're on Framebuffer and the GL, which is the graphics library. Okay, Julia, thanks for coming. I'm sorry you're still sick. Anybody know who these guys are? Watson and Crick, no. Close though. Steve Wozniak, Steve Jobs, right? And this is the Apple II that they're working on. Remember, the stuff that you're doing for this class is basically the kind of stuff that Steve Wozniak, Jobs didn't have much to do with the technical part of it, but Wozniak was the brains behind the whole thing. But you're doing stuff that's very similar to what he had to do in the 1970s to get all this stuff working, because he basically had a processor that he put some memory next to and some other input-output ports, and then had a keyboard connected to it, and he had to go there. So think of yourselves as like reliving history in that sense. Remember, this is what we're, like the big picture here, right? We've got this Raspberry Pi, we've got an ARM processor and memory, we've got peripherals, which are the GPIO pins that you're all used to playing with now, the UART, which is the serial port, which now you can do printf to the serial port. You've got timers on there, and you've got the keyboard that you're now doing. Remember, this is just an overview again, right? Assembly language that you spent some time on, not too much more right now. C and pointers, lots of stuff on pointers, especially for Malloc and so forth. Functions in the stack, you guys know all about that. And the rest of this is just kind of more of bare metal stuff. And remember, we're like most of the way down at this point, right? We've gotten most of the stuff. Actually, we have done most of the stuff already in here, except for the graphics stuff, right? And then one more. Remember, we're trying to become better at this stuff. Force Awakens, right? We're trying to become this. I don't know if you remember this one. Is this from the most recent one? I think it's from the most recent one where, sorry, spoiler alert. Rey actually becomes kind of Jedi-like and uses her force powers and whatever. And if you haven't seen the Star Wars ones, they're pretty decent movies. All right. So how does data, in other words, visual data in this case, get from your Raspberry Pi to the monitor and back again? So there's some back talk of the monitor. It has to tell how big it is and has to do some description, but basically it's a connector, and it's this funny looking connector like this. You've all hopefully seen them before, at least you will. But it goes in this port on your Raspberry Pi, and it has a clock. Oh, we know about clocks, right? And it has some data lines which are going to pass various data bits, which is the pixel information about the colors and so forth. And then there's some other control things in there to tell what it's doing, go to different modes and whatever. There's also other things built into the HDMI standard, like security and so forth, and which makes it a little hard to do some things like capture video off of a stream from somewhere, because there's security involved. The good news is you do not have to worry about any of that. Okay, the Raspberry Pi handles all of the details of the HDMI transaction. So that's the good news. It's already built in for us. We would not want to really write that stuff. It would be kind of ugly, much like some of the other stuff that we've already written is a little ugly. But anyway, that's that. Now, the pixels themselves, depending on what sort of thing you're outputting to, they actually can look a little different. You guys, I don't even know if you remember old CRT TVs, the ones that are like big and they're long, whatever. And the pixels on there are very different than the pixels you might find on a, well, actually, they're not too much different than like the LCD ones. They're in a slightly different form. But they can be, depending on the thing you're outputting, they look a little different. But the key part of a pixel is there's 3 colors associated with it, right? There's a red, a green, and a blue pixel. And if you remember anything about your physics, where light, you've got 3 primary colors of light, which are not red, blue, and green, right? Those are red, blue, and yellow, which is what you learned when as a kid, which isn't even true anyway. What are the primary colors of paint? Magenta, cyan, and yellow. And if you don't, and that's they should make kids paint sets out of magenta, cyan, and yellow, but they don't for some stupid reason. But anyway, the light colors are additive. In other words, if you take red and you add red light and you add green light, what color do you get? Anybody remember? Yellow. Yeah, you get yellow as it turns out. If you add green and you get and blue, you get cyan, and if you add red and blue, you get magenta. That's why they end up being the primary colors of paint, etc. But anyway, there's 3 primary colors here: red, green, and blue. And when you mix them, you can get lots and lots of other colors based on how much percentage of each light there is. Okay, so that's how it actually works in there. And by the way, there's various channels here which send all the blue, and the other channel sends the green, and the other channel sends the red, and so forth. And it's all digital. Okay, there's no more of this analog business. It's all digital data. Okay, the pixels themselves. Okay, by the way, here's the color that we were talking about. And if you mix blue, red, and green, you get white, as it turns out. Okay, they're additive and they produce white light. Famously, Isaac Newton figured that out in the 1600s. But anyway, the pixels themselves, this is just a grid, right? That's what the pixels are. Who did the Photoshop project for 106B? A few of you guys? Yeah, some of you guys did it. Or if you did the Photoshop, well, if you didn't, that's all right. But it's basically a grid of data where each pixel is a particular color made up of these 3 other colors. Okay, that's how the data works. All right, and as I said, you've already seen the light one there. Okay, the frame buffer is a buffer, and we know what buffers are now. They're just locations in memory, and the frame buffer is the image that's located in memory on your Pi. We're going to talk about where in memory it's located in a few minutes, but it's just a 2-dimensional array of pixels, which means you can put parrots and you can put various other color bars and whatever you want. And you just have to modify the memory location with new data, and it changes the pixel. We're going to see that as well. So it's kind of cool. Okay. Our pixels, as it turns out, are 32 bits. Oh, that's nice, right? All of our ints are 32 bits, which is kind of nice. It's made up of 4 different parts. It's made up of a red, a green, and a blue, and then an alpha. What does the alpha mean? Anybody know? Yeah. Brightness? It's not quite brightness, actually. Generally, yeah. It's transparency, yeah. For this class, as far as we're concerned, we're always going to make alpha the maximum opaqueness, which is FF, as it turns out. If each one of these are 8 bits, each one is 1 character in hex, right? So 2 hex characters, 1 byte. FF, and you can make those. We're always going to leave alpha at maximum. You can play around with that if you want, especially if you're a final project. But for now, just know that it's FF. Okay. So the frame buffer is a particular thing on the Raspberry Pi that you can manipulate and you can access and so forth. Okay. And you can read what we call the physical size, the virtual size, and the pixel depth. Okay. So let me run a quick program for you on a Raspberry Pi. It's called video, which is not this one, it's video. Okay, make install, and it's going to run. Hopefully, there we go, it's going to do it. And the Did this change? No, nothing changed there. All it did was it read some details about the system, about the actual frame buffer, and it gave us some interesting information here. It says the ARM memory, that's the processor, is from 0 to 80000, and then it says GPU memory is from 800, and then I'm not sure what this one is. I thought that would be the upper value, but it's not, so I'm not even sure what that one is. But it tells you what's the physical size in number of pixels of the display, okay? And then it says virtual size. And notice that the virtual size now is 2 by 2, okay, which is interesting. And then there's also 16 bits per pixel, which is you can set how many bits each pixel actually does use. And on here, it turns out that the Raspberry Pi, if you do a 2 by 2 like this, it tries to merge the corners a little bit. So this is actually a 2 by 2 picture, even though it looks kind of like blended. It just does that kind of automatically. And at this resolution, it looks blended. At a very small resolution, it won't look blended. But it just does a little bit of blending in there if the pixels don't match up. But so this actually is red, yellow, blue, and cyan is what they've actually got on the monitor right now. That's the way it's currently set up. Okay, this is what it looks like. There it is, red, yellow, blue, and cyan. And you've got the physical width, which is the amount on the monitor, and you've got the virtual width, which is the actual, like, kind of in what you consider that you've put on the screen. And it can be a little bit different, okay? And then in this case, it gets interpolated and then blended and whatever. You don't need to worry too much about the details, but if you notice blending, think to yourself, oh, maybe there's something going on with my difference between my physical and my virtual. You'll see, yeah.
Is it physical width the size of the monitor or the size of the display?
Well, it can depend. It's generally the size of the actual display part that you see. The monitor can actually have more pixels in it. So like this one, like you kind of noticed, it's like there and there, right? Did it say, I forget what it said on the, let's see, it said that the physical size was 1680 by 1050. This is, I think the monitor can actually support more than that. It might be that the Pi can't support more than that or something like that. I'm not 100% sure. Good question, though. All right. So how is this frame buffer set up in memory? You can go look at this up in the table, but this is what it actually is. It's a struct, or you can map a struct onto it, which we like to do, and it has all these fields in it, which tells you some of this stuff. If you're the Pi, you can actually write to the width, height, virtual width, and virtual height. So you can actually change those yourself. Okay. You can't change what's called the pitch, which is the bytes per row of the frame buffer. We'll get to more details about that later. The GPU does that. Now, when I say the CPU and GPU do that, there are actually two processors on your Raspberry Pi, right? There's the CPU and the GPU graphics processor, which handles all the graphics stuff on the monitor. Two different processors. They're eventually going to have to talk to each other through things like this. We're going to talk about how that happens a little bit later. Okay, and then the depth, you can say how many bits per pixel of the frame buffer you get. And then this is interesting. We'll talk about this at the end of class. This is the offset of where the screen lives in the frame buffer. We'll see why that becomes important later. Okay, this is actually pointing to where the actual frame buffer is. It's the GPU that determines where that is. Okay, and then the size of the frame buffer, same thing. The GPU says, here's how big your frame buffer is. And then you say, okay, I'm going to say that it's in that memory, here's where the data is for the pixels. Okay, so there's some amount of memory in there like that. Okay, if you want to configure the frame buffer, okay, you can set the physical size and you can set the virtual size and you can set the depth, right? And you have to read the pitch, the size, and the pointer. And we can do that. I'll show you the actual code to do that. That is here. All right. So in here we've got, oh, look at this struct, right? This is the struct that we just declared or talked about on the last page. Okay. It's nice that it's a struct. We can just do memory onto that like we normally do. Okay. And then there's this interesting like frame buffer FB, which is the frame buffer. It turns out you have to align it to 16 bytes. That's what all this garbage does in here. It aligns it correctly. And then we're just setting some things. Okay, we're going to say, okay, it's a 640 by 480 with a depth of 32 bits per pixel. And then we're going to call a function called mailbox write. We will get to what the mailbox does a little later. For now, just know that the mailbox write like does this handshake between the CPU and GPU, and it transfers data over to it. Okay, and then we do a mailbox read to get more data back. We basically write to the frame buffer and say, here's our information, and then we read it back from the GPU and say, now you tell me what you've got to do, and then that will do it, and then it's going to print some of this stuff out. So let's see that in action. Let's see. See if that will do it. And uh-oh. No. Oh no. You guys, what's that? That was my reset button should have worked, but of course it didn't. Hang on. Let's try again. There, now it's going. There we go. Okay, so it's okay. The error, it will return an error message if something's wrong. And remember, we set 640 by 480. We also set the virtual, the 640 by 480 and the depth. And then it said, or then we calculated the size. And then it came back and said, this is the pitch, which basically is the width times the depth. Okay, or I guess we got what did we get back? The depth from it. And then this is where the pointer is for our frame buffer. Once we do that little handshake, now we go, oh, now I know where I can write my data. All those red, green, and blue pixels, I can put it in that location there. Okay, and an offset from there. It's you'll see. Okay, so that's it. Did anything come up on the screen this time? Oh, it went blank. So I probably just blanked it out because it wasn't. Things changed on that. Okay. All right. So there's I showed this one actually. There's shared memory, as it turns out, between the frame buffer and between the CPU and the should say GPU, not CPU and CPU. Let me change that right now. CPU and GPU. There we go. Not GNU. Okay. The shared memory between that. Here's how it looks. Okay. We basically have, remember this area from here to here is your 512 megabytes that you've got for your Potluck. That's how much memory you have. Now some of that memory is going to be used for your programs and your CPU. The rest of it gets to be used for the GPU. Why do we need so much? Like 256 megabytes seems like a lot. Well, it's because there's a lot of data involved to write millions of pixels onto the screen. You need many megabytes of data to do that. Okay, but that's how it's set up. So there's just a break there. And we can use that information to know that we're going to put pixels in the top part, and it will write to the screen once we set everything up all right. Okay, how do pixels work? Well, pixels are, as I said, red, green, or blue. Okay, and an individual pixel can be it's a full 4 bytes. Okay, 1, 2, 3, 4. Generally, we say this is our RGB A, red, green, blue, A. In parentheses up here, notice it says BGRA, right, which is kind of the reversed part of that. Okay, what that's all about is little endian versus big endian. If you look at the first byte in our number, it's going to be the blue byte. The second byte is green, the third byte is red, the fourth one is alpha. If I read this out as a number, it would come out reversed, which would be the RGBA, right? So if you read the number out and look at it, it will be backwards from what you're expecting. If you read 1 byte at a time, it will be the BGRA. So again, you're gonna run into that issue when you do this assignment next week, and you'll go, what's going on? It seems backwards. It is backwards because if you read 1 byte at a time, you'll get it in this order. If you read the whole number, it pulls the number out in little endian format, meaning it reads it that way. So you just got to kind of know that, okay? And by the way, here's what red would look like. No green, no blue, no green, full red. And we're going to always say that the alpha is also full. That would produce a red pixel. No blue, full green, no red, full blue, no green, no red. And that would be blue. See how that works? Okay? And again, don't forget this little endian business here. It comes to bite you sometimes. Okay? All right. So if the frame buffer is just an array, okay, we can figure out how big it is by doing unsigned char frame buffer. If we want a 2 by 2 pixel frame buffer, like the one that came up when we turned the Raspberry Pi on, 2 by 2 by 4, because each one is 4 bytes long. Okay, so that's how many bytes you would need to store a 2 by 2. That makes sense? Okay, And then if we want, we can set them like this. The blue we can set to be 0, the green we can set to be 0, the F we can set, the red we can set to be FF, and the alpha we can set to be FF. What color is this one going to be? Red, right? And so that's it. And these are all the different ones down there. Okay. One sec, Kurt. The top left of the screen is 0, 0. Okay, so just like you might think of a regular array, which is kind of nice. Question?
What was the 4 for again?
What was the which?
The 4
The 4. 4 bytes per value,
Okay.
right? Because you need 1 word's worth to, or 32 bits worth. Okay, question?
Is this like a double array, or?
That's such a good question. Is it a double? Like, is it a double or not? In this, and we'll get to the interesting thing about that in a minute. Is this like a 2-dimensional array? No, this is just a 1-dimensional array. Okay, but on the screen it will map based on how many rows and columns you have. So the 0th one will be up. Well, sorry, this is 1 byte's worth. But if you had pixel 0, it would be up here. Pixel 1 would be here. Pixel 2 and pixel 3. Does that make sense about that? Okay. And if we do it with unsigned chars, that would do 1 pixel's worth. Those 4 lines there. Okay. We're going to see it later where we can do it as an entire, like 1 int at a time. In which case we'll do each pixel will be a little bit different. We'll get to more details on that in a bit. That's a good question. Okay. All right. So again, well, this is kind of the same sort of thing, right? You have to do a little bit of math if you want to figure out the x and y coordinates in here, right? You have to do the total amount for the 4 bytes per value times the x value plus 2 times the y value, and that's the number of rows. So you have to do a little bit of math in there if you want to figure out where on your whole picture you are. Okay, so you got to think about that, and it's not hard. It's just a matter of thinking it through. Okay. All right. Here's again, same sort of thing as what you would do for this. Okay. You would actually, if you wanted to do it 1 character at a time for each individual pixel color, this is how you would do it. Okay. We will see a little slightly different way in a few minutes. That's, I think, a little easier to understand once you figure out what it means here. Okay. And there you go. This is a let's see. FB of unsigned now. FB of width times height, right? This is now unsigned is how many bytes? It's an unsigned int, by the way. 4 bytes, right? So if we set the first one to that, then what color is that going to be? Red or blue and green. Should be blue and green gives you what? Cyan, right? Okay, and then, oh, you know what? I think this is actually backwards again. When it's in this form, it's backwards. This is backwards. So this is, let's see, RGBA. So red and green should be yellow in that case. Yes?
If your A value is 0, would it be invisible?
If your A, say again.
So
Oh yeah, if your A value is 0, it should be invisible. Yeah, it should be just full transparency, which would be blank basically. And I think it just ends up being black screen behind it. That's what happens. Or whatever's behind it, something else. Well, it doesn't really make sense to have something behind it. It's a little hazy. I don't know all the details about that. Yeah, Archie.
So then is this? This one would be back because all the F's are in the.
Yeah. So in this case, right. This is now in little endian format, which means the little end we said was A, so it's going to be RGB. No, it's backwards. You know what? I think this might be wrong, actually.
I think some might be. Yeah, except when it's written as a number, then it's not.
When it's written as a number, the least this one ends up the highest in memory. Right. So this does end up the highest in memory. So this is highest in memory, meaning this is the blue. Right. So BGRA. Yeah, RGBA. No.
isn't
BGRA. Right. That's right. So yeah. So this one would be A. What did I say? Blue, green, red. No. RGBA is what it is. Yeah. Right. RGBA, right, so it'd be RGB, so this color would be blue. Right? Hang on. Let's go back and check. Hang on. I just want to make sure that I'm not lying to you here. Back here. Oh, okay. Right. It's interesting. They BGR. Yeah. So this is not I thought it was a reverse of it. It's not, is it? Interesting. Well, we'll have to play around with it and see. We're gonna try it and see in a minute. Okay. We're gonna try it and see. All right. Let's actually do this first. Okay. I'm gonna show you some more code. Clear. We're going to try to just clear the screen. Okay. All right. Here's how we're going to do that. Okay, we're going to make it a 640 by 480, and we're going to have a depth of 32. Okay, I'm going to set the width to be the width and the height to be the height, and then we're going to say the virtual width and height are the same. So there's hopefully no blending going to happen here. Okay, the depth is going to be 32 bits per pixel. The offset into the frame buffer is 0, so it's just going to be straight into the frame buffer. The pitch is going to be, it's going to set that the pitch is going to come back from the GPU, and the frame buffer location is, and the size is. Okay, all right, so we initialize some things, and then we have we initialize it by doing this. We've got the mailbox write and the mailbox read, and then we've got that, and then we will print out the values, and then we're going to do this. Okay, so this one is blue. So here's, okay, this I know is blue. Well, we'll check in a second and see if it's blue. If this is blue, this is going to be BGRA. So, okay, there's the definitive one. Okay, it is B this way, then G, then R, then A, when we write it like this.
But it's reversible. How do you do that?
Well, I'm gonna. Well, oh my gosh, you're right.
Why don't we? Can we put in red?
Yeah, we'll try both. Let's try both. That's a good question. All right, hang on. You're right. It's reversible. I didn't even notice that. Oh man. Okay, hold on. Make install. Hang on. I want to make sure that. Oops. Okay. We are going to do this. I'm going to make install and see what happens here. All right. Okay, so it is blue, but that doesn't help us because it's reversible. Let's figure it out. Let's try to make it red. Let's say, what if we make this red, that, and then this, and then this? Let's just see what it ends up coming out as. It'll either be what or what. Oh, it might be transparent. Yeah. Whoops. Hold on. There we go. Let's try it. Let's just try it. See.
I guess if it comes out as a color, we know that it's not.
Yeah. Okay. So it's cyan. Okay, hold on. So.
Well, I mean, would be right with the alpha at the very end.
Yeah, but then
Switches the ending. So alpha.
Is it cyan? It's hard to tell from this angle. Let's figure it out. Let's do the other. Let's see.
it doesn't make sense that it's not just like either red, green, or blue.
You're right. It's not making sense right now. Okay, let's try doing this. If we do, we'll figure it out, right? Eventually. Let's see.
That's what I think.
Come on.
Try it.
Okay, this is magenta.
Try doing the same thing, but with the first.
Okay, hold on. So,
I think the alpha is 0.
yeah, you know what? I think the alpha's 0
I
too,
don't think the alpha.
and I don't think it's going to affect it in our case. Yeah, I think in our case it's not going to affect it. So I'm not sure. Is that what you were saying, Skylar? Yeah. Okay, so let's just make install again and see what happens. Hang on. Okay, and yeah, all right. So, what did we figure out? Okay, the alpha's the first one, and it actually doesn't matter, is it, for whatever reason. The next one is what?
Wait, if you set it to a value other than 0, will it affect?
Red. So let's do this. Make this one.
Chris,
Oops.
as your friend Katie said to you, transparency is a sham.
Yeah, transparency is a sham. Exactly. Okay, so if I do this, assuming this is the alpha, then this is red and green. This should be what? Yellow. Let's find out. By the way, you can look at all this code. So if you forget this, just go run this again and figure it out again yourself. All right, it's yellow. Okay. All right. So I think we have figured out now. Tom.
If you write something other than FF, will it be like a shade?
Yeah. So it's good. So Tom said, whoa, what if you write something other than FF? What is 127 divided by 2? About 64, roughly? 100, it's about that. So let's make this, let's see, 64 in 80 or 80, let's say. That's basically that. So it should be mostly, so it's red and then a little bit of green. Should be orangish, maybe. Let's see. Let's see. There you go. It's orangish, right? Arjun.
If you set the transparency value to something other than 0, will it affect it?
I don't think that it is. It's not 0. It's FF right now. Oh, you mean like?
Like in between.
I don't know. Let's make it 80. All right. Last one. Then we're gonna move on to other stuff. We can play around with this. Okay. Let's see.
No, it's the same.
The same, right? Okay. So it turns out that transparency is not doing anything interesting here. Okay. So if I want to change it, if I want to change it back to,
It's
yeah, I want to change it back to blue.
So the last two
Yeah,
should
the
be
last
S.
two.
And then
And then this one should be 0. Not this one.
those ones
Well, it
can
doesn't
be-
matter.
Doesn't matter right now anyway, right? But that's going to be at RG. Oh no, this one needs
Be
Those
0.
need to be
Yeah,
0.
those need to be 0.
there. What have I done? There we go.
I mean, it doesn't really.
Yeah. Okay. That should be back to blue, right? Okay. That one should be back to blue. Watch it be some other color. Okay. All right. So anyway, we now know how to at least set those. I should have looked in the next thing is there like this. Okay. Now we're going to get into your question about how do I actually. What's wrong?
No, nothing.
Oh, okay.
I think everything is wrong.
Now we're going to get into if we have a pointer into the frame buffer and I want to use my nice bracket notation for a two-dimensional array, how do I actually do that? Okay, well there's some weird syntax here that we've got to kind of discuss. All right, so in this case, if we have an unsigned char FP, that's going to be one long bit of memory, right? And I can actually, and then we could do it this way, or we could, and then we would have to do this whole business with the like depth and everything in there. Or we could say, fine, we know it's an unsigned value. Then this weird funky syntax here. Asterisk FB bracket 2. And then we're casting it to this weird unsigned asterisk with nothing on there, bracket 2 business. What does this actually mean? Well, the question, what we can do is we can check what it means. Okay, so if we go to this website called cdecal.org, I think I might have showed it to you before. It looks like this, and I've actually typed this one in for you already. Okay, if we do this, this means declare FB, that's our variable name, as a pointer to an array 2. All right, is the 2 going to be the width or the height? Any ideas? Let's pause again and just do a little bit of figuring out here. Let's see, 3, there we go. I have a program called testarray. Whoops, testarray.c, there we go. Okay, and here's what I've done. I've basically done something like this. I've said the width is 3 and the height is 4. Okay, so we want a width of 3 characters and then 4 deep. Okay, and I've said, okay, here's our 12 character long array, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Okay, I want to print it in a width of 3 and a height of 4. In other words, I want to print 1, 2, 3. Next line, I want to print 4, 5, 6. Next line, I want to print 7, 8, 9. Next line, I want to print A, B, C. Everybody with me there? That's what I mean by this width and height business. All right. Then I'm going to declare this, by the way, as the same thing here. I guess you've given it away, but this is actually as it turns out, the width. But let's see what happens, why that's the case in a second. I've got 2 loops here. A for loop, double for loop here, that says R is 0, R is less than height, and then C is 0, C is less than the width. In other words, rows and columns. Rows and columns going to the right and left. If I want to print out a character and I want to use the str variable, what do I have to put right here? Figure it out. Talk to your neighbor for a second and figure this out. What do I have to put right here to do this? Talk to your neighbor. Take a second to do this.
Oh, you have to get
Just use it.
R plus. You want?
Is this harder than it should be? I think this is doable, but not that bad. Does anybody have an answer for this? What do you think I should print out here? I'll start you out. STR. Brackets? Can't use brackets in this one. We're not allowed to use brackets in this. If you use brackets, well, okay, you could. Okay, sorry, we can use one bracket. Sorry, yeah, we could also do it with a pointer, but let's do brackets if you want. Okay, we'll do brackets. What are we going to put with the bracket inside the brackets here? Not the bracket. You can't just put the brackets. We want to put this is the inner loop here. Remember, is the columns.
We use ampersand like module.
Nope, you don't use the mod. Nope. Go ahead, Dan. Yeah, R times the height plus C. Why does that work, right? R times, is it height?
Wait.
I think it's width.
Yes.
Close. Why does this work? What is it doing? It's saying, okay, if R was zero, right, we just want the column, which is how far across in the array it is, A, B, or 1, 2, or 3, right? If R was 1, we need to multiply R by how big the width is, and then add the column to that. Does that make sense? You would have to do this math if you had to do it, right? If you wanted to do this, and we'll do it. Now, the nice thing is, if we actually cast it like this to an array with a width of 3, don't you have to know the width to know when to multiply by the width up here? I mean, we're not worrying about how many columns there are here. We're worried about the width. So when you cast this, you worry about the width, which tells you this cast up here says, oh, now, or this type up here says I've got a pointer to an array that has a width of 3, and we don't care how many columns it has. I'm sorry, how many rows it has, how deep it is. It's got a width of 3 columns. Does that make sense? And by the way, that makes this really easy down here. Now that we've got that, if we want to use the matrix variable here, right, what do I have to put in here? Yeah, R and C. Done. Right? And that's maybe how you might think of it, right? The row and the column. Let's test this. Make test array. All right, test array. Ta-da, 1, 2, 3, 4, 5, 6, 7, 8, 9, ABC. 1, 2, 3, 4, 5, 6, 7, 8, 9, ABC. Okay. So, back to what this is all about. Okay. This form here casts this very nicely to tell you how wide it is. So tells the compiler how wide your array is, so that you can actually use the, well, you can do it this way, or we can we can do it with the double bracket notation in there. Okay? In fact, I'm not sure why we didn't do the double bracket notation there. That should have the double bracket. And that depends which one you're using there. Either you use the first one or the second one. In this case, I think that should be the second. Oops. Well, I'll fix it for the slides themselves. Okay. All right. Let me actually show you. Let's see. Let's show you where this. I have one here called. Let's see. Where is it here? It is 4-color. Okay. All right. Here's what I've done. I've said, okay, I've given this. All right, I have assigned the pitch variable, I'm sorry, the IM variable rather, the IM variable to have this particular pitch, which is the number of, which basically tells you the bytes, the number of bytes to words, so you have 32 bits per word in here. And then I've said, now I can say, all right, IM 00 is this number. And what did we say this color was? Red, right? The first one's the alpha, so it's red. And then this color is going to be red, and blue should be red, and green, thank you, should be yellow. And then this one is red and just blue. And then this one is, this one's going to be red, green, and blue, which is cyan. That's the one that comes up when the pi starts up, okay? And it should do this. I've also put a little delay in there so you can see it in action, and you can see what happens with the blending. I put a 1-second delay in there. So let's see how that works. Okay. Red, yellow, blue, cyan. And it just kind of melts them together like that, right? I wonder if this would be where the transparency might come in. Should we try something? Why not? Let's turn all these FFs into let's just see what happens here. I don't know if it's going to do anything, but now they are blended, so maybe you never know. Let's find out. Did anything change? No, I don't think so. Okay. All right. Experiment failed. Okay. All right. So let's actually look at another program called the grid one. Okay. Here's where we're going to do the same sort of casting in order to get our size here. So that will be very nice. Okay. And then we're going to draw some pictures on here. We're going to draw a horizontal line, okay, which basically is going to, let's see, draw a pixel. So we have to look up our draw pixel. Here's our one-dimensional. We've got our two-dimensional draw pixel, which is the one that we like the best, right? And it's going to basically, let's see, draw it like this and just put that pixel in there. Okay, we're going to draw a horizontal line, which is going to go through the x values. We're going to do a vertical line, the y values, and we're going to see what happens. We're going to do this a couple different times, not different ways. Let's see what this actually comes out to be. There we go. Ta-da! This is like a nice little grid, right? Because we've got horizontal and vertical lines. Okay. There's another fun one in here. Let's see. Where is it? C-bars. C-bars is like this kind of stuff on steroids. Vim cbars.c. It's got all sorts of like kind of funky stuff in there. Make install. I like this one because as an older person, I've actually seen this picture before.
Oh my God.
Right? Ever seen that before?
Yeah.
That was used back in the day so that you could tune your television to be the right colors. Like they would put this up at 2 in the morning when nobody was actually watching TV, and this would show up on the TVs, and you'd be able to like change your TV to be the right colors, and you kind of knew what the colors. You could get like a thing that said what they should be, and you tune your TV to be like that. So kind of fun. You can look at that code if you want to. Okay, so here's an interesting thing. This is where I think I'm going to have to put it up on the screen itself as we go along with this. If you write directly to the screen, what happens is it actually flickers a little bit. Okay, it's an odd effect that happens when you put a value straight on the screen. It actually makes the whole screen flicker a little bit, which is really annoying. Okay, what you have to do to combat that is this thing called double buffering, which means that you basically draw the picture in a place in memory that's not being shown on the screen. And then you switch the frame buffer to say, now look at this whole piece of memory where the screen is. And it does it all at once, and there's no flicker, as it turns out. Okay? And then you just draw to the other place and swap it back and forth. Okay? You basically have two buffers, the back one and the front one. Basically, the one that's being shown is the front one, and the back one is the one you're drawing to. Okay? And then you swap them when you get to it. Okay? Which way is best in memory? Remember, memory is one long array. Would we rather have our memory broken up like this, where this is the front and this is the back, then this becomes the back and this becomes the front, or would we rather have it like front, back, front, etc.? Which way in memory makes the most sense? Think about that for a second. Anybody have any ideas?
Can you rephrase the question?
Yeah. So we've got a memory block that's going to hold two buffers in it. Okay? And it's basically one long set of memory. Do we want the first buffer to do we want the memory layout of our buffers to be such that the memory goes from here and then here and then here and then here and then here? Or do we want it to be here, 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 etc.? Which one do we want? Abba, what do you think?
The second one, I think.
This one?
Yeah.
Why?
Because I don't know. I don't really know. It just seems like.
Well, let me ask you this. Go ahead, Julia. Yeah. Let's think about drawing the first bit of the first row in our picture. If we have it like this, we draw the first row and then get to a place in memory where the second buffer starts. We have to jump over all that memory to draw the second row, jump over all that memory to draw the third row, etc. Meaning that our two pictures are now like spliced into memory, which is probably not what we want. As Julie was saying, she said, look, in this case, if this was the way the memory was, that would be the first row in memory, then the second row comes right after it, then the third row comes right after it, then the fourth row comes right after it. Eventually you get done with the first picture, and the second time when you want to do the other buffer, you start here, one row after the other. This is actually the one you want, as it turns out. Okay? That's the one you want there. Okay? And again, we're going to display the front buffer and the back buffer. This means that you're actually using twice as much amount of memory to hold your information, but it makes it so it doesn't flicker, which is really annoying. Okay? And you guys have to figure the math out for this for the next assignment. Okay? Basically, you use this offset. I don't know if you remember that was one of the pieces in the data in the struct that we had. We've got the offset, which tells you where the memory is where in the frame buffer you're going to start drawing from, which is kind of nice. You just need to update this, tell the frame buffer, oh, redo it, and it'll go to the other one, right? So that's the offset 0, right? This would be x offset is still 0. The y offset, though, is the vertical height, and it starts it right here, and this is the picture that gets shown while you're drawing in this one. And then when you show this one, you draw on this one, and flip, 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 flip. Julia.
More memory efficient if you just had, like, rather than copying all the contents of your front sheet back to, like, just swap the pointers?
You actually do exactly that. You swap the pointers. Now, you do have to keep these in sync with each other if you're like updating them. So if you're writing one line of text down here, right? Up here, you'd better have this whole buffer already to write the next line of text. You do need to copy back and forth. but you're absolutely right. It's just a pointer swap in terms of the overall, like how you go from one to the other. Perfect. Yeah, Tom.
If you're like trying to display maybe like a video with high frames per second, do you have more than 2?
If you're trying to do video with high frames per second, do you want more than 2? Not normally, because you can switch fast enough that you're just going and drawing the other one. But you would be switching back and forth between them, drawing one frame while the other one's being shown, show the other one, draw the other frame like that. Okay. Let me show you the different. Yeah, Pierce.
I'm wondering, would it be possible instead of having like 2 separate buffers, to send only the changes to the image and have it display the changes themselves?
You could do that, but that causes a flicker. I mean, basically, that's what's happening. You're not going to have 2 different buffers in this case. If you tried to update it on the screen, you'd do that. Let me show you the example of the flicker. Now, I'll try it on this one and see if it comes out all right. Let's see. What do we want? We want single buffer. Make install. Okay. And the code you see doesn't have the details in it because you're going to write that. I'm showing you the one where it has the here. Okay. This is what it's going to do, and what it's doing is it's writing "Hello World" on the screen, one after the other, after the other, after the other. It's just updating. It's writing "Hello World" and then clearing the screen, writing "Hello World" and clearing the screen. Does that look good? Can everybody see it? If not, I'll put it on the big screen. Can you guys see it from there? Okay. But anyway, it does not look good because it looks like lots and lots of flickerings going on. Okay. If we look at the double buffer one, watch what happens when we're doing the same exact thing except doing the swap properly. Okay? All right. There we go. Hello World is actually writing a 0 and a 1. That's the only flicker you've got there. Much, much nicer when it's doing that. Okay? Every time you wrote a new character to the screen. Wait a minute. Have we even talked about how to write characters to the screen? Can you see that says Hello World?
Yeah.
Oh, we get to write characters to the screen. Right? But right now all we know about is pixels. Okay? How do you draw text? Well, okay. So first things first. This is actually what we call anti-aliased, which means that there's like gray pixels in here and black pixels and almost white pixels and things. Turns out most text that you see on your screen is anti-aliased, which means that it looks better to your eyes. It's like there's some blending going on there. We are actually not going to do the blending. We tried it a couple years ago. We tried doing the blending, but it turns out you need so much more information that when you type make install, it takes like a minute to install. And people are like, this is crazy, we don't want to do this. Even though it looked a little nicer, it's fine now. It turns out it looks fine, but we're not going to do that. So this one looks like anti-alias, but we're not going to do that. But what it means is basically we are going to give you, and we actually give you a very compressed version that you have to figure out in lab, but it's not too bad. Once you figure it out, it's like, oh, okay, that's how it works. We'll give you a compressed version of each character that you're going to be able to print out. And then what you're going to do is you're going to take that character and figure out how to write a function that basically puts a character on a screen at a particular location by drawing each little pixel in there, right? If it's 0, and it's only going to be 1s or 0s. So if it's a 1, you draw a black dot. If it's 0, you don't draw a pixel, right? Or I'd rather the other way around. If it's 0, I think if it's 0, you draw. If it's 0, you don't draw anything. If it's a 1, you draw a white pixel. I think that's what you do. Okay. But anyway, that's what's going on. Notice this way, if you have a width per character, well, this is XY. That's the location of XY. This is just X plus WY because it's offset and same Y location, etc. Kind of makes sense how that works? Kind of cool that we're drawing text. And that's what you're going to be doing for the next assignment too, and then it actually puts text on there. You are welcome to create your own fonts if you want. I'll have to find the file that used to create it to compress it, but you could, if you wanted, make whatever fonts you want. We just happen to use a font that is kind of normal in that sense. Okay, all right. Remember I said there was a mailbox in there, and I said, oh, we'll get to that mailbox later. The CPU and the GPU have to talk to each other. Okay, the CPU and GPU have to talk to each other. Remember we've got the memory at different locations in here. And our CPU is going to be writing to memory, and the GPU is going to be reading from memory to put it on the screen. And there has to be some communication there because you don't have the ability to sync them up directly. It's just hard. They're both running at different clock speeds. They're completely different processors. So you have to be able to talk somehow. Let's talk about how they talk. It's actually much simpler than you might even imagine. This is not simple. This diagram is not too simple. But basically it says there's a bunch of, let's see. I guess this is basically just showing the RAM itself in here and where the physical memory is and so forth. You do not need to memorize this diagram. Okay, but the mailbox here is used to do this communication. Okay, the CPU needs to set some settings and actually put the data on there. And the GPU and CPU need to agree on where the frame buffer is, and they have to agree on these things. The problem is, when does the GPU know that the CPU is done? Or when does the GPU know that the CPU is asking for anything, like to give it back data? You have this very, very simple handshake. It's a single bit, that's all it is, one bit, that actually says, I just sent you a message in your mailbox, or in the mailbox. And it basically says, I've set this bit, which means I've sent some data to you. I have put some data in a memory location, go look at it. And then the GPU, when it reads it, it sets a bit that says, I've replied to you, go look at it. It's just a mailbox back and forth, and that's what they call it here. Okay? So the memory is shared, and then you've got this mailbox location here. This happens to be where the mailbox location is. Okay, and you can actually see this in mailbox. I think, maybe not. Hold on. It is in clear mailbox. Mailbox. Maybe? Hold on. There it is. Oh, no, it's not there. Ah, they're lying to us. Hold on. I know it's there somewhere. I'll find it. Find dot dash name mailbox. There it is. FB. Oops. Mailbox.c. There. Must have it open somewhere else. We're going to delete it. Okay. So this is what it actually looks like. All right. If you want the mailbox to be full, you set that bit, the bit on. If you say the mailbox is full, you set that bit. You can also say the mailbox is empty by setting a different bit. Okay. And then another struct here that tells some difference here, that tells some information about all this stuff. And then you have the mailbox write function, which will actually use the mailbox base location, which I showed on the screen before, and it actually sets it. It has to be volatile. Why does it have to be volatile in this case? Yeah, the GPU is writing to it, or maybe the CPU is writing to it, and you can't just tell. So again, the C program would be bad if it just ignored that variable. All things like this one right here, while mailbox status. Remember, that could change by the GPU, not you. And it will do it. And then it ends up, you write your data and do that. And you can also read from it as well using basically kind of the reverse process. Okay. You won't have to write the mailbox code itself, but you will have to use the mailbox in your code. So you do have to kind of understand how that's working. Okay. The CPU mails message, and the GPU does the same thing and replies. Question, Ben? No. Okay. All right. Here's the format for this. Okay. You've got a read value. If you read from this value, it destructively reads. In other words, it resets it. You can also just peek at it if you want to. Okay. It's got some other ID and some configuration information in here. It's also got some, like, these are the 2 bits we care about. Those 2 bits. The rest of this word is just kind of whatever. We don't know what it is. It's undocumented. If you can figure out how to use it, great. I don't think it might do anything. We don't even know. They don't tell us this in the stuff. And this is from that mailbox.c program where we kind of already saw a little bit of that. Okay, that's how the mailbox works. Okay, here's the overview. All right, the GPU refreshes the display using the frame buffer, right? The frame buffer is the location in memory that's shared by the CPU and GPU, right? And the CPU puts data there, and the GPU ends up getting it onto the screen. Okay? And by the way, why doesn't the CPU do that? Why can't we just make the CPU do that? Any ideas? Yeah, Tom?
It's busy writing.
Yeah, it's busy writing, right? If the CPU had to take care of putting all the data on the screen, well, then that would be time away from us doing our processing, right? That's why we have the GPU on those. GPUs are purposely made so they can put data on the screen really fast, okay? In fact, they're purposely made because, I might have mentioned this in 106B if you took this from me, if you're trying to do a two-dimensional picture on the screen, what is the big O notation for a two-dimensional loop? If it's n by n. N squared, right? Do we like n squared algorithms? No, we don't, right? Then try to think about three-dimensional drawings. Now you've got an n cubed algorithm, and it's even worse, right? So in this case, we want to build a GPU that purposely is able to handle problems like n squared type problems very well. Turns out that it's because pixels are each pixel is roughly the same, you can have a different mini processor, called a core, inside your processor that actually handles each individual pixel, let's say, or a group of pixels at a time. And you can do it, you can actually make it much faster than your CPU would be able to even handle it. But there's two reasons we have a GPU. One is so the CPU can do its thing, and the GPU can just take care of the memory. And the second thing is the GPU is purposely built because of the problem of putting the data on the screen. So that's kind of nice. All right. Size of the image sent to the monitor, that's the physical size, okay? That's the actual physical size. The size of the frame buffer image is called the virtual size. The virtual size, remember, would be like 2 by 2, but then what gets sent is like the full amount, okay? And then we said that they share, and then there's this mailbox in here, okay? All right. You guys are all going to put all this together eventually. Right? And I showed you this on the first day of class, what you're going to actually end up doing. You're going to become this person here, right? Where you, let's see, do I have the shell in here? No, I don't have the shell in there. The shell is the one that you're finally going to create. It's going to put characters on the screen. It's going to use your keyboard that you're now building functions for to actually input data into your Pi. And then it's going to take that data and actually put it on the screen like characters and so forth. So it's a fun kind of culminating sort of thing. And then after the frame buffer, we'll have more information on the frame buffer on Monday. After the frame buffer, there's like one more thing you need to think about. I'm not going to steal the thunder of that lecture, but there's one more big thing you have to think about getting all these things to play nicely together that we will talk about. And then you guys are ready to do your final projects. So we're almost there. A couple more weeks of this, and then we're into our cool final projects that you'll enjoy doing.
How many more assignments?
How many more assignments? We're on assignment, what, 5 right now?
Yeah.
5, so there's 2 more. There's the frame buffer, and then there's the interrupts one, which is the last one. And then you're done. Yeah. And it's not that bad. Interrupts aren't that bad. Don't worry. They're not too bad. They're not too bad. Although, I will say something about, so if you don't even know what interrupts are, that's okay. I will say that the interrupts live at memory location 0, which means that if you've got any null pointer dereferences in your code, you will end up squashing the interrupts, and then all your code will break on that last assignment. So sorry. That's the not quite as fun part of it. Okay, we're a little early. I don't think. Does anybody know who what's his name? Edward Tufte is? He's a guy who's famous for putting together cool graphical descriptions of things, maps and graphical descriptions of things. And I saw a talk from him, and he said once, nobody will ever complain, ever in the history of any like lecture or anything. Nobody has ever complained if you end a few minutes early. So hopefully we won't complain if we end early. Feel free to come out for questions. I hope the Malik finishes up great for everybody, and then keyboard, keep going on that. I will see you guys Monday.